Okay. So let's start the last lecture of the day. Professor Vitto had on 2D van der Waals heterostructures.
Okay, thanks for the chairman, and I sincerely apologize. I was trapped a little bit by the traffic jam in the way. So let's continue today's session. Since I was trapped by the traffic jam, and you guys had a few more minutes to relax. So today, let's say we're gonna say something about, except for graphene, other developments of two-dimensional materials, including like transition metals like hydrogenides and other systems. Basically, let's start with some 2D long-range ordering first. So we reviewed that in the history of the whole experimental development of two-dimensional systems, that the first exploration of graphene was happening in like early 2000. And then 10 years later, there was a heterostructure ever made of graphene on BN. And then another 10 years later, we have obtained a beautiful, topologically non-trivial Chern bands. And there were fantastic physics, like fractional or integral anomalous quantum Hall effects. And all these are one of the line which is developing rapidly in the past 2 decades. But there's also another line. If you remember, we mentioned at the very beginning of this course that graphene is gapless. So for real application, it might be not very useful because we want to have a transistor which is working either on a very high resistive state or on a very low resistive state. So people started to, let's say, shift from graphene to other two-dimensional semiconductors. And at the same time, around 2010, there's also a lot of studies focusing on the opportunities of two-dimensional long-range orderings. So the long-range orderings apparently it's just some kind of interaction, and then you have some phase happens at the ground state. For example, if the spins they exchange with each other, and they can have some magnetic ground states, either ferromagnetic or anti-ferromagnetic, and etc. But at the very early ages, theory predicts that we mentioned once that two-dimensional magnetism should not be existent because they did some vigorous calculations theoretically. I couldn't even find a photo of Herbert Wagner. The two authors made a statement in the 1960s. This paper was so famous, and a lot of people just bought this story and believed that two-dimensional ferromagnetism or whatsoever should not exist. And apparently this is not the case, because in 2017, several groups independently start to investigate from the bulk material of a magnet and explorate that thing down to a very thin limit. And these are several pioneer works on two-dimensional ferromagnetism, or let's say magnetism in general. The two very famous ones are the back-to-back publications in Nature. The one is from Xiaodong Shi's group in Washington University. The other is from King Fei Mak in Cornell, if I remember correctly. So what they did is they managed to find a very thin flake of one of these compounds called chromium germanium telluride. In short, it's CGT. And the other one is actually a chromium triiodine. So these two compounds, they show very distinct behaviors under their magnetic ground states. One is ferromagnetic, which is soft magnetic. You see there's no coercivity field in the x-axis. This is actually the magnetic field. And it saturates very rapidly, and there is no hysteresis. So this is the typical behavior of soft ferromagnets. And this compound, on the contrary, this is a bilayer system, shows at zero magnetic field. For example, the bilayer shows a zero net momentum. This is curl or RMCD movement, which is optically probed. And at some magnetic fields, one of the layers is flipped over and they all point up, so there is a net spin polarized at the positive magnetic field. On the other hand, the bottom layer flipped downwards, both are pointing down, so there is a negative negative moments. This is a typical anti-ferromagnetic behavior, and each of the layer is an Ising ferromagnet. So that's the single layer case, and that's the bi-layer case. So this is a very first example, the two papers, two in a row, published in 2017. People started to be thinking about maybe there was something doable in many circumstances to investigate those two-dimensional spin-order systems. And indeed, so if we look into the history of spin interactions in 3D models, there were several very typical examples. For example, there's Heisenberg interaction, which includes the Ising model, the XY model, and mean field, etc. There's also the indirect interaction, and which can be drawn in several different cases, including this super exchange, double exchange, and RQKY. These are well known since a very long time ago in 3D cases for all these ferromagnets. And experimentally, most of these examples of spin interaction models are found experimentally in 2D. But there is some cases still missing so far. So, for example, the RQKY interaction have not been demonstrated in two-dimensional magnets so far. Otherwise, all these compounds, they found themselves a specific interaction type in this, and according to the three-dimensional spin interactions. And there was something which in 3D people could not play with, which is, again, the rotational degree of freedom. For example, some theory predicts in 2018, if you have some a special arrangement of the top layer and the bottom layer of two types of ferromagnet materials, there should be some skirmion, which is in real space topology of magnet vortices showing up. Also, there is one typical example done by spin polarized STM, which means you use a magnet tip to probe the sample surface, because the tip itself is spin polarized, it interacts differently with these domains or spins downward in the substrate. So what they found is that by just choosing, they managed to find different stacking orders, which the top and bottom layer is the same thing as the previous examples of chromium tridiodine. And this thing is showing different stacking order. I mean, the atoms are arranged just differently by shifting this top and bottom layer. Then the spin polarization of the whole system changes. And this is the first evidence that actually people can, by keeping one of the material, the spin interactions the same, and combine the two, rotate with against each other with some certain angle or some shift or displacement, the total spin interactions can be changed drastically in the resultant system. And that's a very good example of how people can manipulate by this stacking order of a certain material, which is having a ground state of magnetic ground state, and then at the end the total magnetic behavior changes. And also there is another optical measurement showing that actually in this CRI3 system, it can be found some second harmonic generation in a non-reciprocal way. So non-reciprocal means they define in their system that there was some inversion symmetry breaking, SHG generation in certain family of materials, and this non-reciprocal means this SHG generation were induced by external magnetic fields. There was some deformation of lattices, and then there is a huge SHG signal enhancement in the system. So this is also, people found that the spin ordering in 2 dimensions can be very funny in both, for example, the spin structures in terms of the lattice rotation with each other, and also the optical responses, like nonlinear behavior. And there's also a big family which is very interesting as well, which is topological magnetic materials. And many of them are actually Van Waals material. They are layered compounds. You can isolate them down to very thin flakes, monolayer, whatever you can. And this is a very famous material called manganese bismuth ferrite. And this compound, according to some experimental investigations, they have very complicated magnetic bases. And especially when you have this material put in under the ground state and upon some kind of vertical electrical field, the system can be tuned as a field transistor. At the meantime, the magnet phase can be also tuned. For example, this one is a IXY, which is a Hall resistance, and the colors are representing different gate voltages. So basically, it's a field effect transistor. And the x-axis is the external perpendicularly applied magnet field. And we can see that at some gate voltages, which is very negative, like minus 200. And this IXY, we call that anonymous Hall because basically, if you have a system which measures the IXY, and by inputting some current in the longitudinal direction, if you have some signal in IXY, which is non-zero, while B is zero, that means you have obtained some anomalous Hall effect. Notice that there is no Q in front of this name, right? Because it's not quantized usually in many magnetic thin films. It was observed a long time ago. No big deal, but if you look carefully in this material system, at some certain gate voltage means you have to put the Fermi level of the system down to a certain depth, to, for example, in the Hall side or whatever. Then this anomalous Hall plateau becomes quantized. They are actually minus 1 h over e squared. So this, although there were some reminiscence like 98 or 97%, not quantized at b equal to 0, but at least it saturates very rapidly. So this is defined by the authors in this paper a quantum anomalous Hall effect. So this is QAHE. That means we have a quantized H channel, which is topologically protected, and that can happen at b equal to 0. So this is very important because, as we talked about yesterday and the day before, in many like two-dimensional electron gas systems, if you have to obtain this quantized plateau or H channels, you have to have low temperature, high mobility, and high magnetic field, right? So to have this kind of quantum anomalous Hall effect, people can avoid one of these parameters, so you don't need B anymore, which is very convenient for constructing further devices. For example, if you would like to couple superconductivity, if the Cooper pairs can be injected, providing that, then you can have parafermions or myriad bound states without any external magnetic field. And that's one of these advancements. And so far, I would say the system that shows QAHE, we already, I think, discussed a little bit, but let's count again. I think there are at least more than 5 systems. Oh, there's one of these, and there's a topological insulator doped by magnetic dopants. There's our current system, which is topological magnet, which is layer compound. There's also a graphene system, twist double layer graphene with one layer aligned with HBN. So that breaks is the C2T symmetry, and these can also demonstrate quantum anomalous Hall effects. There's also a famous experiment done by Kim Max group in Cornell, and that is tungsten diselenide and molybdenum diselenide twisted at the 0 degree limit. So they also show integer quantum anomalous Hall effects, and there is again later on that an ABC graphene, which is a little bit different from the twist by graphene. That you don't twist anything. Right? It's a rhombohedral stack by itself, and if you break also some symmetry breaking, you can have quantum anomalous Hall effect. And now in 2024 or 2023, there are new systems coming out which shows even fractionally quantized Hall effect, including MOT2 twisted by like 3 point something degree. And also we have 5-layer ABC graphene, which is a pentalayer rhombohedral system. And I think that's pretty much what we have so far. Many of them. It's not a big deal anymore that people have been dreaming in early days that topological insulators, they want to find something without magnetic field, which is quantized automatically at the zero B field. Please.
Quantum Fold effect requires very big magnetic field, right? Several Teslas.
In graphene, several Tesla?
In general, in 2D material.
Yeah, depends on temperature and sample quality, yes. Several
My
Tesla
question is,
good
when you have anomalous quantum Fold effect, you don't have extra magnetic field and you still have effect. Does it mean that your 3D material produces this strong magnetic field?
Inside.
Yes, so if you don't have extra magnetic field,
yes,
that means that your 3D material creates magnetic field that is strong enough to absorb the effect, or how does it work?
How does that work? Yes, yes. So because in the back of the origin is very the same, because I think we showed some slides yesterday. So everything we care about is various curvature. So you define some various curvature, whatever function, and you make an integral along all of this Broglie-Lewin zone. And if this thing gives you a non-trivial value, like non-zero number, that Chern number defines your system, which can be like topologically non-trivial or not. So in the graphene conventional quantum Hall effect or any kind of two-dimensional electron gas, you don't have a various curvature, very strong topology in your system, but you need an external magnetic field to create that. So external magnetic field is effectively playing the role here. And if you have some system like this, they are not high mobility anymore. They are actually flat Chern band. The band are very flat, and the Chern numbers are not really, doesn't equal to zero. So there the mobility, you don't talk that anymore because the effective mass are very large. So basically, you can say the mobility is very low even, but they have a non-zero, non-trivial Chern number due to this topological phase, various curvature and various space inside. So in this flat band system, like most of them are the case. You don't need that anymore. The real magnetic field inside, you have a fake one, like pseudo magnetic field, which plays the role. So it's two different systems. One is the conventional one. You need a high mobility, high quality, and the width of plateau depends on a lot of parameters. But in the topological systems, although they don't require any external magnetic field, but they are very low temperature so far. So the highest temperature for realizing these quantum anomalous or integer quantum or fractional ones are like below 10 Kelvin. So still very low temperature, and people should be, continue looking for higher temperature topological orders in any kind of systems that can allow us to have more relaxed experimental conditions. But it's already very, very promising because a few years ago you don't have many systems. There is only one. Like a long time ago, the sample is grown by MBE, which is very rare, and the doping sometimes works, sometimes does not. And now you just go there, just treat the sample, make the contact as good as possible, and by trying several times, you will get that in any kind of labs. So it's really some breakthrough in kinetic matter physics. So let's say this as a hallmarks for topological edge channels, and it might be very promising for building future quantum computers or qubits or whatever, which is not my field by the way. But let's continue these two-dimensional spin orderings in device applications, the direction, let's say. So since we have material that is easily exfoliated into like atomic thin layer, and then they have different magnetic ground states, they can be coupled just by stacking each other. For example, the well-known is exchange bias in AFM and FM 2 layers. All these tunneling magnetic junctions can be made. Instead of using conventional thin films, people can now do very easy like desktop experiments by just stacking materials, whatever you want, and then you can demonstrate the old school spin valve phenomenon. And some of them are actually showing huge spin polarization rate. For example, in this experiment, It's the same material. Monolayer case is Eisen ferromagnet. 2 layers Eisen anti-ferromagnet. In this case, if you put down like 4 layers in a row by putting like another top and bottom electrodes, this is a typical MTJ, magnetic tunneling junction. All right. So there are several steps that switches each layer of the spin polarization. At the end, they saturate toward the one direction. And if you calculate this spin filtering rate in TMR, it goes up to like 20,000, which is huge. But anyways, it's some kind of estimation. So the window is rather narrow, anyways. But this is a good example of saying that two-dimensional magnetic materials can be somehow useful. But another, on the other hand, that all of them have very low magnetic critical temperature. For example, all of these known materials, none of them are stable at room temperature so far. So all these studies are still like bounded, limited at low temperature and for fundamental researches. For future applications, there are a lot of barriers people have to climb up. For example, you have to find a material which is stable, which has a magnetic transition temperature above room temperature, and you have to be able to mass produce that thing, and for application, industrial application. So there's really a huge long way to go. So far, it's still in the, let's say, in the laboratory scale. And also, we have a very good example showing that by combining these two-dimensional materials with the different magnetic behaviors, people can use the old method, which is called SOT, spin-orbit torque. So this spin-orbit torque happens like in this diagram. If you have some material, for example, it's platinum or tungsten, the conventional ones with a huge, large SOC, which is spin-orbit coupling. And here what they use is a new compound. It's called tantalum iridium telluride. The last one is 4. I think it's a 114 phase. And tantalum iridium telluride gives also very high spin-orbit coupling, so that as long as you pass the current in the bulk, it will be automatically be spin polarized towards up and down surface, so that you have a spin polarized current flowing in the top surface and in the bottom surface with a spin direction differently aligned. If you revert the direction of current, the whole spin polarized current will be reverted too. That means if you place another magnet on top, and as long as this current is strong enough, the spin polarization of the current will influence the spin polarization of the material placed on top of that. So that means it allows us to tune the magnetic moment flipping by injecting current through SOC material. And this is how they obtained as the Kerr microscope. You can see directly the whitish color means they spin up, and the grayish color means they spin down. Just by changing the direction of current flows, you can manipulate the spin states like conventional people have done that in thin film physics. So everything in old school physics can be reproduced in two-dimensional materials. So they have some advantages, which is allowing us to get rid of this lattice mismatch between interfaces. There are some disadvantages as well, because many of them still have very low TC or TN, and means no temperature for anti-ferromagnetic materials. So these are the state-of-the-art of spin orderings. And there's one more thing we have to mention is that, since a long time ago, people are looking for transistors, which is having not only the charge degree of freedom, but also the spin degree of freedom. That is let's say, a semiconductor which is magnetic. A magnetic semiconductor has been dreamed by scientists and researchers for, I think, several decades, but nobody has ever managed to make any kind of spin-filled transistor above room temperature so far. So that's a huge challenge. But at least we can try at low temperature and study the fundamental physics. This is no problem. So, for example, this chromium germanium telluride system, people found that by tuning this Fermi level using electrical field, the magnetic curve, the loops can be tuned in terms of shape by changing this saturation magnetization field and the corrosive field. And there's also a demonstration that by using a heavy doping method, for example, this liquid gating method, and the CGT material can go up to 300, and it shoots up a little bit, it's reaching there 300. But in terms of any kind of real application, it's still not very useful so far. At least to create a record of gate-tunable semiconductor behavior, ferromagnet is a good example. And after reviewing this long-range ordering of magnetic materials in 2 dimensions, there's also, of course, ferroelectricity in 2 dimensions, which supposedly in 3D case are this long-range ordering of dipoles, like dipoles in molecules or other kind of materials that align themselves, and you can flip them by applying a vertical electrical field or in-plane electrical field, depending on the direction of these polarization dipoles. And it was supposedly not possible in 2-dimensional limit because there is a depolarization field theoretically superimposing on all kinds of thin films. But actually people managed to find that there are some examples which people are able to see this ferroelectricity at room temperature or low temperatures. This is one of the examples. So alpha indium selenide 2-3 phase. And this is itself is a semiconductor. You can see that you just fabricate the device into a MOSFET structure, you will have a field effect curve. But if you do the PFM measurement, which means piezo force microscope, you can see that the surface can be written by polarizing the electrical field vertically to the sample. So it can be really indeed tuned into negative or polarized, positive polarized cases as a ferroelectric material. But if you measure this field effect, you will see that there is a huge hysteresis window. This hysteresis window, according to these authors in this paper, they are coming from this ferroelectricity in the material, which I would say is questionable, but at least it demonstrates that this window can sometimes be used as a memory, because if you go, for example, at stage 1 and you somehow go back at the same voltage, the stage 1 becomes stage 2, which shows you that you don't change any external thing. For example, you go to 0 and you swoop up and go back to 0. The state of the resistance or the current will show you 2 levels, like low and high. So this is a typical possibility for building up memory transistors in this case. And then there's also a very strange system I would like to also introduce you, even though I'm not a big fan of that, but it has been a really huge topic. A lot of literature has been and are talking about sliding ferroelectricity or moire ferroelectricity in 2-dimensional heterostructures. The first paper, I would say experimentally, the big one, the high-impact one, was published by Paolo's group in 2019. And what they saw is that as long as you have the graphene flake placed on HBN, and if there's an alignment of the HBN underneath, you will have a huge hysteresis in the field effect curve. That means the direct peak is shifting by itself up and down, and they prove that this is not charging purity. And by carrying out various structural devices, for example, without alignment, with alignment, and they change the swooping speed as well, to make sure that everything here is actually a ferroelectricity behavior. And what they claim this is something unconventional in their title. And then there are some theoretical papers that to follow up. And even before this experiment, there are already theories considering the 2-dimensional heterostructures. For example, they define this potential by twisting or displacement of 2 layers. And there's a word called sliding ferroelectricity. Depending on the sliding distance or the displacement between the top and bottom layers, you will have different polarization potentials for the layer. At the end, it will be very, for example, prominent effect even in 3R structure, which is the rhombohedral. So they claim that this is a general behavior which is universal. You should have this sliding ferroelectricity as long as you have this 2D monoid structure or the 2D rhombohedral structures, and which has been to be true, but actually the polarization field is very low. For application-wise, I would say so far I couldn't find any real application potential for that. But at least for fundamental physics or fundamental research, it's very interesting. For example, there's a paper coming out in 2023, and people have done some measurements locally on this Waals pattern by just changing this vertical electrical field from positive 1.4 to negative 1.4 volt per nanometer, which is a large number actually. 1 volt per nanometer is huge. This goes to gigavolts per meter, right? So this is a huge electrical field applied to the surface, and then this, at the very beginning, this orthogonally cross line becomes like a breathing mode. They are expanding and shrinking, and they claim that this is agreeing very well with the models behind, and it's one of the supports for the existence of sliding Fourier electricity in two-dimensional heterostructures, for example. So in 2D heterostructures, we have ferroelectricity, we have a possibility to play with spin orderings, and without a heterostructure, a single layer, they can also demonstrate spin orderings and ferroelectricities. That's something, let's say, conventionally people never thought about that before. So it's developing very fast in the past few years, and that's why I'm bringing up these topics to you guys as a review of this course. And of course, except for this spin ordering and dipole orderings, we should have also two-dimensional superconductivity as another kind of orderings. So this is also something people have been doing that since a long time ago, especially in thin films, like disordered thin films, clean thin films, a lot of them. And people have found that thickness dependent of disorder depending can tune the ground state of the superconductivity into metallic state or insulating state. So there is a bunch of theories considering the MIT or SIT transitions, the superconducting phase transitions, quantum phase transitions at the ground state, many literatures. But now, the two-dimensional superconductors, let me say, they provide us a new opportunity, because in one sample now, you can tune the Fermi level, you can change this mean free path, which is correlated to this superconducting coherence length, for example, or the material itself, some kind of intrinsic parameters, so that you can tune in situ within one sample without doing tens of samples. Within one sample, you can have the ground states from superconductor to metal to insulators. So this is a very good platform of materials for us to investigate 2D superconductivity. And one of them, their properties is the so-called Ising superconductor. So in many kind of two-dimensional materials, especially TMDs, they have this so-called spin valley blocked property. So each valley and each spin, they like to be bound together. Like minus k is always spin up, plus k is always spin down, for example. And this kind of spin is Ising type, so they point always up, out of plane. And if you apply the magnetic field perpendicular to this superconductor, for example, the superconductivity is killed very easily. So these are two examples for MOS2, gated by ionic gate. And also another example of niobium diselenide. There is no ion gate, it's just a solid gate. And both of them show, for example, if you have a perpendicular magnetic field, the superconductivity will killed very rapidly. But if you apply your external magnetic field parallel to the plane, to the AP plane, it's so robust that it's a lot of times higher than the Pauli limit. You know, the Pauli limit in BCS theory is defined by 1.8 something times TC, right? So it's pretty low, for example, for niobium diselenide. It should supposedly to be 1. A few Tesla, and actually the superconductivity are persisting up to 6 or 7 Tesla. This is not Tesla, this is 6 or 7 times higher than the Pauli limit, which means more than 10 Tesla in this case. This is in units of Tesla. We can see people went up to 50 Tesla, and the superconductivity is still there. The in-plane superconductivity, in-plane application of external magnetic field doesn't kill the superconductivity. So this is one of the very specific properties of 2D Ising superconductors, specifically for TMD materials, for example. So this we have to also mention once. And there are, of course, after reviewing all the long-range orderings, there are several types of materials, ferroelectric, magnetic, superconductors, and all the materials some of them should be able for application. So why we keep on talk about application of them? Because a material, if you really want to be, let's say, developing sustainably in the long term, you have to find some really useful, let's say, killer application for them. And what people have been thinking is the quantum information application could be one of these directions for two-dimensional materials. And that's how people try. I believe that Benjamin Sesame has already introduced you his system of like combining superconductors. In his case, I think some kind of a germanium or something like that, high HC material, and then combine these superconducting electrodes with the existence of quantum Hall H state. You should be able to create some new physics, like different pairing mechanism. And in the future, let's say, let's put a futuristic point of view, should be able to give us some opportunity to create Majorana bound states like that. And there's also a possibility to create quantum dots using 2D material, because quantum information among this possible material platform of quantum computers, quantum dot is one of it. And indeed, many two-dimensional materials can show that, but actually it's not a big deal, because as long as you have a small enough system which has the discrete energy level, you should be able to see that. And that's how it was investigated in the history. And also we have qubits made of two-dimensional materials. This is one of the examples coming from Casey Group. This is not from Casey Group, I'm sorry. It's from other group. What they did is they just used these STEs encapsulating some kind of graphene inside of it. And they use Ramsey measurement. They obtained some lifetime of a few tens of nanoseconds, which speaks that there is a possibility to build up quantum qubits using this two-dimensional materials, but the lifetime is extremely low in this case. And Casey's group showed another example. For example, what they did is not using the material directly as a Johnson junction. What they do is use the material instead of doing Johnson junction, and make a large capacitor for this transmon technology. And this niobium diselenide, 2 layers with the HBN in the middle, plays the role of capacitor. And this gives rise to the functioning of two-dimensional capacitor-assisted transmon platform, which shows lifetime of about 1 microsecond. So we know that the state-of-the-art transmons has a lifetime, for example, if they're using aluminum Johnson junctions, a few hundred of microseconds. And for the phase qubits, it's even longer. So this is still some very infant stage. This is one of these possibilities people are thinking of using that. But except for using two-dimensional material directly for a qubit, they can play their roles, for example, for these external circuitries of quantum computing or qubits. For example, the one in the previous slides, in these circuitries, there's some kind of amplifiers, very literally written there, low noise, low temperature, low noise amplifier. So this is a very useful amplifier for reading out, because using this kind of radio oscillation or whatever technique, these readout signals are often in the range of gigahertz, so which requires a low temperature, because the whole thing is placed at low temperature, especially for Johnson junction qubits. And then we have to amplify the signals to read out and get a good signal-to-noise ratio. So for doing that, people are using these kind of low-noise amplifiers. Basically, some of them are built by high-mobility filtered transistors at low temperature. Some of them are built by superconducting parametric amplifying techniques. So these things, for example, if someone can find a high enough performance of two-dimensional materials, and it can also play the role of amplifying, so which is also a direction for application. So I would like to also to break for a few minutes in today's lecture, and we'll come back after a few minutes. How about that? Yes, this.
Да нет, это вообще не базовая. Тут вообще не вспоминать. О, давай так. Тут зовсім інша штука. Я пойду. Тут дуже складно. Думаю, це не так складно, як думаю.
А до речі, я завжди була програма. Я тільки все розкладаю, я завжди роблю свою програму. Так, і йому треба знати, що воно хоча б складно перевести. Але це ще буде. А, ну так. Ну, йому треба взяти, щоб було всіх хоча б одне.
Я бы так. Не вірю в те, що точність це імовірність.
Ну, я думаю, що це моя думала іншу спосіб. Пиши. А скільки береш? Яку найменше?
Найменше? Ні, це ж трошки всі. Якщо я візьму 47, то теж але тому 46. Чому? Тому що не першому сигналі можна залишити ще 4 пакети, так може 46.
Але вже є другий варіант. Щоб кожної було на 5.
Це лише значення, все, в мене припуск.
I need to talk to No, yes, my supervisor.
No, yes.
Yes.
But that's a good place. That's fine.
Shall we continue? Okay, guys, welcome back, and let's continue. So, the introductive documents about all these two-dimensional systems have been almost, 85% finished. So the last part of this kind of communication between us will be some introduction, finally, for two-dimensional semiconductors. And semiconductors is one of these key components for our modern technology. And undeniably, that everyone is using that, and it's very critical for our daily life. And two-dimensional semiconductors, however, they are still catching up. They're finding their way towards some kind of useful future. Let's have a look. We have been talking about high-performance two-dimensional semiconductors before for several slides, And there were some kind of theoretical considerations who wants to calculate everything and to predict all this possibility of having high mobility materials. Why high mobility is important? Because again, if the system is not ballistic, in the Drude model, sigma is defined by carrier density times electron charge and this carrier mobility, a very simple linear equation. So the letters are very small, but we can see some typical values over there. This is 1,000. 1,000 mobility are considered to be, let's say, quite good, especially if this value is measured at room temperature. You know, in silicon technology, it's only a few tens. Like a few tens is already very good for many applications. And these are basically intrinsic mobilities calculated. This paper was published in 2023, but you can see that there are some tungsten sulfides and molybdenum disulfide is sitting down there with only 100, but apparently they appear to be wrong because this material, MOS2, we'll show you later in the coming slides, can have very high mobility at the low temperature limit, up to a few tens of thousands. And experimentally, there are already some kind of system of 2D, because as long as you have a two-dimensional electron gas, and as long as you have a high enough mobility, which means long enough coherent phase coherence time for the electrons, they should exhibit quantum Hall effect. And indeed, we mentioned once in the previous sections that black phosphorin and other compounds in 2 dimension can show quantum Hall effect. And today I'm going to review with you guys some kind of elementary 2-dimensional semiconductors. So except for these compounds, we have also elementary ones, which is very interesting. Let's have a look. There's 2 families, nitrogen and oxygen families. And we have phosphorus, arsenide, antimony, bismuth, telluride, and this kind of selenium, which seems to be possibly to be semiconducting, and all of them have a property of low melting temperature when they are at their solid phase and ambient condition, let's say. So they have some kind of common properties: low melting point, semi-conducting, and they are located in very in adjacent places on the periodic table. So experimentally, people started exploring these 2 columns of materials, and the first one they found that in black phosphorin, and this thin layer of phosphorus can show phonon-limited transport, that the mobility saturates below like 30 Kelvin, and you have 4,000 and 5,000 centimeter squared per volt per second mobility, and this is high enough because a few thousand is good enough for us to see some quantum oscillations and quantum Hall states. This is published in 2016, the first elementary 2-dimensional high mobility semiconductor. But the drawbacks of this material is black phosphorin is very good because the band gap is so good that the optical guys love it. It has been used for many optical measurements, like photodiodes and things like that. But the material is not very stable in air. So you have to encapsulate always everything in a glove box, and you have to put HBN encapsulating on top of that. And this is the common feature of elementary 2D semiconductors. There's a second example of black arsenic. Black arsenic is just the one below phosphorus, and people found that the band structure is slightly different. And there were very funny physics of Rashba values. What they call Rashba is because there are spin-orbital interactions in the system. And indeed, this system shows a very odd sequences of Landau indexes, and it has been studied in 2021. And this is also an example of few-layered elementary 2D semiconductors. Also, people studied another elementary 2D semiconductor called tellurine, which is telluride in a few layers limit. And they have several phases. This is one of the phases which shows rather high mobility. And we can see that they are actually formed by van Waals chains in 1D. If you look perpendicular to the screen, They were like small chiral chains in one dimension, and they are bounded into two dimensions. So we are expecting a huge anisotropic behavior in the system, which it is. But if you measure correctly along some certain direction, and you fabricate devices out of that, you will see also rather high mobility in the system, up to 6,000 for tethering. So there are these elementary semiconductors are very interesting. There is a recent one also showing a very, let's say, specific way, unusual method to fabricate two-dimensional elementary semiconductor. Because we know that all these elementary ones, they are very unstable. They are having low melting point. So the surface energy is supposed to be very large when they are very thin. So what they've invented in this method is that by encapsulating a bulk in two HBNs and heat them in situ and let them recrystallize themselves after cooling down, the material will become from a bulky stuff into a thin layers. And everything happens in 2 layers of HBN and locally. So this is a new way to grow a single crystal system in a local, some kind of, encapsulated environment, which is very funny, interesting. So you see that the compounds has turned from the bulk stuff into layered compounds, and people did some STH oscillations inside of this system. But unfortunately, in this material, the gate tunability is very bad. You can see that the gate voltage is from -70 to 70. You have only a tiny shift of this frequency of STH oscillations. Anyways, this is also an example of elementary two-dimensional semiconductors. So these families are so far largely unexplored, and future studies in monolayer limits and other kind of studies would be interesting for the future. And then we'll come to another second family, which is transition metal dicaprodenitic semiconductors. And this is one of the most advanced materials ever in two-dimensional semiconductor materials. So the first paper was published in 2011 by Andrakis in Switzerland, EPFL, I believe so. So he managed to exfoliate a very thin MO2 material down to the monolayer limit. And if you have a look, the monolayer MO2 actually has a very, very high contrast. It's very visible. So it's around 0.6 nanometers. And compared to graphene is almost invisible. It's only 2.3% of absorption. And this MO2 is easily visible, but very difficult for exfoliation. You cannot have large flakes easily compared to graphene because the material is very brittle. Okay, and by just fabricating into a MOSFET structure, Andrakis obtained a mobility of 200 at room temperature. And it got commented by some other researchers from Columbia University because in the calculation there were some parasitic effects. So actually the mobility is a few tens only, but still it's very high at room temperature among all these known two-dimensional materials. As a semiconductor, gap one is already wonderful. And also in TMDs there's an effect called speed value locking, we just discussed a little bit in the previous slide. And if you go to this paper, it will show you how it works. Eventually, it's just a very simple principle that you have, for example, a band structure of, for example, an SOC material of TMD. And this SOC breaks this energy degeneracy into this kind of manner. So in this valence band, you will have a little gap between the two nesting bands. But in this connection band, the bottom, they touch each other very closely. So I draw this into a solid line and a dashed line, which is because they have a spin up and spin down property. So this is at one single K. In another K, let's say K prime, everything is just reverted. So we have a dashed line on top, solid line in the bottom, and in this convention band it looks like this. So the shape is a bit flattened. But anyway, so it's a similar stuff, except for this spin up and spin down. So that means if you come with a circularly polarized light, because this circularly polarized light carries a momentum, an angular momentum, and it will predominantly interacting only with this K if your, for example, your light is white and circular light. Let's call it sigma plus. So it will only interact with this K. If you come with a light which is left-handed circular light, let's call it sigma minus, which will then only predominantly interact with this K prime. So basically, if you look at the system in a non-equilibrium way, that if you shine a circularly polarized light to the surface, and if you look, and the valley and spin are polarized, and partially, so the polarization ranges could be very high. And if you look at the system, it will be basically K and spin up using this right-handed polarization. And if you revert the polarization of the light, the system will behave another way. Why? This is why it's called spin-light locking mechanism in the TMD. This provides us a very, let's say, useful way to tune the value or spin just by light. Okay, so it can be very useful in many kind of operations. For example, people do excitons and other tuning things in the TMD system, or heterostructures made out of them. This is a huge branch of condensed matter physics, and we're not going to too much detail of that. So then we will talk about some kind of opportunities and challenges in two-dimensional high-performance semiconductors. Again, let's come back to this 2D high-performance semiconductor. When we say high performance, we have to have, for example, large enough mobility, either electrons or holes, and we have to have also a very good off and on state. So the ratio between them, between the switched off and switched on, has to be large. And this is representing the on-state current. It's a measure of ion, and this is a ratio between on and off states. And this materials has to, behave in a stable manner, cannot react by itself or degrade by itself in air. So we would like to have something stable and conductive, which is easily switched off and on. That we call a high-performance semiconductor. And let's see how people are looking at that. And because two-dimensional materials, especially TMDs, they are nowadays very scalable. That means you can easily grow them. Like we said at the very beginning, when people grow graphene by chemical vapor deposition method, this can be done for TMD materials too. You can easily grow large-scale, like wafer-scale films and transfer them using the wet transfer method or whatever method onto different arbitrary substrate. This is an example. People show that in the flexible electronics, and people can fabricate large-scale ones. And also people can grow at layer-by-layer ways that you can control the number of layers. For example, if you would like to have a wafer scale, like 6-inch, 8-inch, whatever, and if you tell them to tune some parameters of the growth, they can give you specifically a 2-layer, fully covered wafer, or 3-layer or monolayer fully covered. And that is also very important because a layer sometimes is determining the physical properties of the material itself. And this is also one of the advantages of the mass production. Since they can be mass produced, that's why it's more, let's say, reliably, we can believe that they will become useful one day. This is one of the steps towards success. Okay, and there's another one paper showing that by using this MOCVD method, and the whole thing can be grown at a low temperature condition. This is a polycrystalline. So the homogeneity is solved also. If you measure the sample over like thousands of them over a wafer scale, all of them are behaving very coherently. So you have the same starting point of switching on and similar on current. Only a few of them are away from this statistics. So all these are very narrow. So this is also a good sign that maybe two-dimensional semiconductors can be really useful because they are available to be mass-produced. And there's another thing, except for the mass production, and except for this looking for the high performances, we have to solve the problem of some kind of this fabrication. because ohmic contact to two-dimensional semiconductors is very difficult. So the ohmic contact means when you have a sample, you measure the IV curve across the source drain. Your IV curve should be linear, which is ohmic law, right? So if your sample is showing some kind of nonlinear behavior, it's very likely that you have a contact barrier in the system, or the material itself is not very conductive. So there are several pictures showing that by whatever means to contact two-dimensional material, you have always some kind of contact barrier. For example, if you put the metal on top, you will have a van Waals gap, which is defined by the vacuum, and then you have a Schottky barrier. If you put something hybridization, the material and this metallic contact, you will always have another Schottky barrier plus some metal-induced in-gap states. And people found that sometimes you can do the contact by just side contact, which is 1D, quasi-1D edge contact, which is really possible for many kinds of two-dimensional materials. Even in this case, sometimes people can solve the contact, sometimes the contact is also showing a barrier over there. So that's why, ever since the first paper published by Andrakis in 2011, till very late 2018 or 17, none of the devices can stably show a method to give a linear transport at low temperature. And that is because the contact material is not idealized. So let's have a look at the literature, how people were trying to solve this problem. This is a PRL paper from Ensling group in Switzerland. So what he did in his group was try to put some kind of MO2 directly on top of platinum contact. So they put platinum first, and then use AFM to clean it, and transfer a layer of MO2 on top. In this way, they can have some kind of high-quality samples. They have seen some kind of SDH. Not very bad. But the reproducibility, I'm not sure, because the publications using this method are very limited. And then there is another paper coming from MIT Zheng group, and I think Lansley from Hong Kong University. What they found is that actually using this bismuth, a very low melt temperature metal, you can diminish this contact barrier between MF2 and this metallic contact. And what they obtain is they have very good performance of IV curves, and unfortunately, in their paper, they just investigated the system down to 70 Kelvin. So they didn't measure anything below. We don't know why, but at least this is a good sign. Bismuth can be a good contact. And later on in 2023, there's another paper coming from Nanjing University, China. So they found that actually using another material, which is antimony, and specifically they use a 0,1 -1,2 surface. So I don't know if they found it accidentally or they predict something from theory and they started experiment. Anyways, at the end, so 0,1 -1,2 surface of antimony can have a very good contact to MO2 material, and they give the contact resistance as low as the quantum limit is about 40 ohms per micrometer. So this is the two ways that found in literature towards a very good contact to MO2 at room temperature. So even these two papers, they didn't do any investigations down to a low temperature limit, because we know that all these two-dimensional TMD materials, their mobilities are actually limited by phonon scatterings. So if you plot them as a function of mu and temperature in the log scale, they should look like that. So it's increasingly high upon cooling down the sample. At the end, it saturates at some kind of few tens or 10 Kelvin. So that means not only we need an ohmic contact at room temperature, but we also need an ohmic contact below, like very low temperature, 1K or something. So that's something we have to really try hard. And people didn't really use the bismuth or antimony. We don't know why, but there are some other methods. Certain means this method is you just etch the top EM partially, so that you stop right at the surface of MO2 or other TMD materials. And using this kind of surface modifying or bondings between metallic contact and the material, this problem can be solved partially. You can really get a high mobility up to 20,000. You have IV curves very linear at 2 Kelvin and see quantum Hall effect. And this is another paper studying 3 layers MOS2 from Anthony's group again. They're using the same method of pre-patterned platinum underneath the channel. So this is what they obtain. And here I would like to share with you some of our results from my own group that combining some kind of all these techniques from literature, actually there is a way to manage to have ohmic contact in MOS2 at very low temperature down to a millikelvin. So the method is not secret at all, it's just we have to combine several tricks together at one time. First of all, the device has to be made in glove box. So this is to avoid any kind of moisture or adatoms. And second of all, you have to use a window contact method. And the window contact method means it's not edge contact. Instead of touching your layer from the side, we have to put the contact really in a 2D manner, which is touching the material in a large area, so that we have to pre-pattern the HBN at the very beginning, and then using the pre-pattern, the hold, you have several windows open on the top BN, and using this top BN with windows, you just pick up your MOS2 and bottom BN and do everything encapsulation in a glove box. So you will have a device that look like that. With this black small color, you have some color contrast. That is because there is no HBN in this small window. That's why you have a color difference in the contact area. And the third thing is you should never use an E-beam evaporator. We don't know why. You have to use a thermal evaporator to do the evaporation of bismuth. And then combine the 3, that is glow box, window contact, and the thermal evaporator, you'll have the contact, ohmic contact like a charm, down to very low temperature. This is how it looks. So you can see that this is the let's say field effect curves of the transistors at the different lengths. We have window contacted one stripe of MOS2, which is in green color, and along with this shortening of channel length, the on current is increasing, which is expected. Then we have a total resistance extracted by this TLM method, and we can measure this residue of resistance as a function of temperature. So even though we cool down from 300 Kelvin down to 1 Kelvin, the contact resistance is always like only a few hundred ohms, never exceeded 500. That's the best contact we can obtain using a very simple method combining 3 tricks together. And then we can have a further characterization at 1.5 Kelvin. Just measure the sample in 2 configurations. One is 4 probe, the other is 2 probe, and you subtract the 2. You will get this contact resistance as a function of doping carrier density. And we can see that except for this border of band age, which is already like in the bottom of conduction band, everything is going up. Otherwise, all this contact resistance is at a reasonably low value, which is below 1 kilo ohm. And the boundary, let's say, defining this 1 kilo ohm above and down is about, say, 10 to the 10 times, 0.3 times to the 12. So below that, it's becoming bad. Above 0.3 times to the 12, it's always ohmic. So this is a very low carrier density that can allow us to approach to the quantum limit. So we can just try to use this formula to convert, for example, in 20 Tesla, how much the carrier density corresponding to when mu equals to 1, right? So this value is just below that, so we can have some kind of ohmic contact even below the quantum limit. And this is a temperature dependence of resistance of the channel as a function of doping, which is gate voltage. You can see that there are some, in the ground state, there is some transition from metal to insulating behavior. And this, the leveling off one is marked by yellow color. So supposedly, according to mesoscale physics, this thing should be like E square over H. It's somehow slightly higher than that. It's probably due to the estimation of aspect ratio of the sample. Anyways, it's very close to what it's supposed to be. And this is a measure of the general properties of this sample. And then we can have a small characterization of this Hall mobility at different temperature. When we plot this is the same thing as the left panel, right panel. The right panel is just we do line cut along different scalar densities. Okay, and we can see that the Hall mobilities can go up to like 10 to the 4th easily in this sample. And the lowest one, which is closing to the band edge, is about 1,000. And then this sample shows very good quantum oscillations at low temperature from 1.5 Kelvin. You can see that it disappears at around 5 Kelvin. So everything, all these the quantum oscillations disappears about 5 Kelvin. So we have to really cool down the sample and measure. If we plot these oscillations, the amplitude as a function of 1/b, we can have another estimation. If where the oscillation disappears, the point defines quantum mobility. That means to have SDH, your mobility is there. In our case, here it's about 3,000. Just 1/b, 0.3 times 10 to the 4th. 3,000 quantum mobility is in this sample at this doping level. Okay, so then we can have a look again. Sorry, the color is a little bit hard to be seen in the back, I guess. But anyway, we can have a summarization of all existing two-dimensional semiconductors from, for example, MOS2 and tungsten diselenide, and etc. So using this bismuth window contact, and the thermal evaporation together with Golovok's sealing, we have obtained the highest mobility ever in all semiconductors at low temperature limit. So this is about 10 to the 5th. So it's like a few tens of thousands. And the hollowed symbols represent the quantum mobility, where the oscillation starts. 1/b is slightly lower, not slightly, just let's say significantly lower than the Hall mobility. There are 2 orders of magnitude. So we don't quite understand yet. Probably there are some intrinsic impurities of the material itself, because the MOS2 in our experiment are just bought from some kind of 2D semiconductors from the companies, and they are exfoliated down to thin layer limit. Supposedly, if you grow the sample with the other method, for example, the flux method, TMD can be cleaner, and that's proven already by studies and literature. So probably the quantum mobility can be higher. But anyways, this is actually not a bad sign, because imagine in our sample, there's no magnetic field oscillation, induced oscillations below 5 Tesla, and still it can act as a very high mobility field effect transistor. So it's wonderful. It's just a hemmed device. High electromobility transistor that has no, not very strong magnet responses in our case, unlike the conventional hemmed metal quantum wells. So this can be actually used as a real hemmed device for example, later on the amplifier at low temperatures. And let's have look at these Landau levels of our device of MOS2 contacted by thermal evaporated bismuth. We can see that the Landau friends are well developed in a linear manner. We can see there's 1, 2, 3, 4, 5 defined by this IXY. That means we can really reach nu equal to 1 quantum limit. And our theoretical collaborator from Flatiron, Valentin Krepel, he did some calculations of a single hyperpole Landau fan of binary MOS2, and using this K.P model, at the end he got this kind of calculated Landau fan, looks like this. There is one specific point we have to emphasize, is that if you look at the color of the Landau levels, they are only yellow and red, which is only 1K, so they come from the same valley. That means the lowest 4 Landau levels, they are valley polarized. In this case, for example, if we shine a circularly polarized light, there might be some possibilities we can block some of these Landau levels, but the experiments are not done yet. So this is just some kind of basic properties. In any case, we have a illustrated diagram on this graph. K and K prime are energetically shifted a little bit, and lower 4 are only from K. And that means all these 1, 2, 3, 4, the plateaus we measure, are from one single value. They are value polarized. And since we're measuring binary MOS2, there are also some other features from off diagonals we don't understand at the very beginning. And by calculation, we finally realized that it's actually coming from the asymmetrically contacted method. Because when we have a top electrode contacting 2 layers of MOS2, so in this case, some of the wave functions are not really probed by the electrode at some certain electrical field, and this can be fully recaptured by simulation. This is a simulation of asymmetrically contacted, and this is a simulation of symmetrically contacted electrodes, so that the off-diagonal features are killed. So we now fully understand the system. Also, we can compare with the binary case and monolith case. In monolith case, we don't see this off-diagonal features as well. So everything is coherent, and if we put the system under 34 Tesla, which is rather high, and cool down the system down to 0.3 Kelvin, you can even see fractionally quantized plateaus. And that's let's say, the very first transport evidence of TMD semiconductors, which are able to show quantization below the quantum limit. And this is not single particle anymore, and this is the feature that we saw that 2/5 and 4/5 are disappearing, let's say, below 22 Tesla. So it's really something that happens at the high field. And there are some other theories from Nicola and Valentine. They built up some kind of loss functions explaining why the 1/3 is missing in our case. So apparently 1/3 is missing probably due to the screening environment of the system, because our HBM might be too thick. So it's something we have to check in further experiments. So 1/3 should be largest gap, right, in this interaction scenario. So with all this, I have gone through all this history of 2-dimensional semiconductors, elementary ones, compound ones, and the high performances in the large-scale production. Probably in the future, also we have found a very easy way to obtain the intrinsic mobility in MOS2, and we found some fractional quantum state conventional ones without topology. This has been also discovered in other systems. For example, Corey Dean, a few months after our archive paper, they posted another paper which measures this valence band of tungsten diselenide, which is P-type. In our case, it's N-type. What they use is another kind of contact method. They use a ruthenium trichloride as a contact, which dopes the sample and the contact, and then diminish the Schottky barrier. So what they saw is also something similar. They saw like 2/3 and 3/5 and 2/5, 1/3. So in their case, 1/3 and 2/3 are there. That's anyway another example of this possibility of having very high mobility TMD materials. And they have also some measurement of capacitance measurement showing its Landau and fractional integer Landau gaps in the TMD system in 2020. But this is not a direct measurement, it's an indirect one. You cannot see the plateaus, you just can see the gaps by the local density of state measurements. Okay, so I would like to appreciate some collaboration from our collaborators. The experiments are done by Suen Zhao, and theories are carried out by Valentine and Nicola, and we have Ning Wang and Jin Zhang for the last part of this presentation. So that's basically the overview of my introduction to the materials to you, and I hope you enjoyed it. I wish you all the best, and I hope you a great continuation of the summer school. And it's my great honor to talk my results and some literature overviews to you guys. Thanks a lot.
Okay, now there is like a lab visit for the non-center World Stefan Institute, so you can just follow me and my colleague wherever.